Hi, in this video I want to show you something that I've been doing lately to improve the visualization of our satellites. So what I'm going to show you here is the Saturn system. So as we zoom into the Saturn system, I'm going to point some things out to you. For example, this is the orbit of Phoebe. Now Phoebe is one of the farther out satellites, and it's got a rather unusual orbit. It's off kilter from the rest of the system, but you'll see that it has several lines here. Now this continuous line here is the actual orbit of Phoebe. So what are the other ones? Okay, so this one here is what we call the ideal orbit, and this one here is what I call the refined ideal orbit. Okay, and neither one of them properly aligns with Phoebe. Okay, and so I want to explain what that means. So the ideal orbit is basically taking the orbital parameters from Horizons. Okay, I'm going to show you Horizons real quick. Okay, Horizons is this amazing system from the Jet Propulsion Laboratory. Okay, so I don't know why I said that. Okay. Okay. So we're gonna generate the ephemeris. So basically, this is what they call the ephemeris. Basically, this is data that astronomers use to describe the orbits of objects. So I've explained this in another video a little bit. It has key information, specifically the semi-major axis, which is basically the distance of the object from the sun, the eccentricity of the orbit, meaning how off kilter it is from the sun, from a circle, and inclination, meaning how inclined is it from the sun's plane, so what they call the ecliptic, and so on. So there's different parameters. So getting back to our plot, excuse me, whoops. Oh boy, what did I do here? Okay, here's the plot. Okay, so basically what I want to show you is that it's off kilter. See, this, when you just plot this ideal orbit, it doesn't match. Why doesn't it match? It's because it was defined according to the plane of the solar system, not the plane of Saturn, or much less the plane of Phoebe. So the first step is to realign it with the orbit of Phoebe. So in this case, we've done that, and that's refined ideal orbit. Okay, so it's lined up, but it's still not, it still doesn't match, right? So we're going to have to do a little work on this particular orbit. I want to show you another one. So this one is the orbit of Iapetus. So here's the actual, I'm going to get rid of the ideal orbit, and I'm going to get rid of the refined orbit so you can see it clearly. So this is the actual orbit of Iapetus from actual data being pulled from Horizons. Okay, now let's add the ideal orbit. See, the ideal orbit is way off. Okay, because it needs to be transformed from the plane of the solar system to the plane of Iapetus. And so that's what the refined ideal orbit does. It basically lines them up. Okay. So let's get rid of the ideal orbit again, and the two line up pretty well. You can see they line up pretty well. Now, why do we want these ideal orbits? Well, take a look. If I get rid of it, you see that it's incomplete. The actual orbit is incomplete. That's because when we plot the orbit of various objects, we may not plot the entire orbit. In this case, we're plotting 1 year. That's kind of the default plotting date list. So I'm plotting from today through 1 year. Well, guess what? Iapetus doesn't make a complete orbit in 1 year. So that's why it's handy to have the ideal orbit plotted as well. Okay, so for satellites with shorter orbits, let's take Titan. Titan's famous satellite of Saturn. Okay, I'm removing the ideal and refined orbits, and you'll see that in a year we have a complete orbit. Actually, we have more than one, because let's find out why. Okay, so the orbital period of Titan is only about 16 days. So it makes many orbits in 1 year. Now, if we add the ideal orbit, it's pretty good. I'm going to get rid of Hyperion because it's getting in the way. Okay, so I'm pulling Hyperion out of the picture. So you'll see that the ideal orbit is pretty good. It looks pretty close from the, this perspective, but the inclination is off. You see how it's tilted? So in order to fix that, we created the refined orbit. Excuse me, not that one. Titan's refined orbit, okay? So now this ideal orbit matches. So let's get rid of the old one. Okay, let's get rid of the old ideal orbit, and the orbit now very close. Not perfect. Why isn't it perfect? Well, because there's other influences that I'm not taking into account. There's what they call perturbations, other gravitational influences from other satellites, and things like that. So it may not match completely, but it's still better, and it's pretty close, so that if we needed to see the full orbit and we didn't have it, we can get a pretty good idea of what it looks like. Okay, so one question you may have is, well, how did I get the refined orbit? And the way we got it was by comparing the angles of these two, and basically taking the ideal orbit and making an adjustment on the tilt to match the tilt of the actual orbit. So when we do that, then you get this so-called refined orbit. That's basically what's going on. So thank you for the video. Here's a pretty picture of the rest of the satellite orbits. What makes these spirograph looking patterns are the crisscrossing of the object as it goes around. The way it's plotted is that makes a line segment between points, and these interior satellites are going so fast around Saturn that in one orbit it goes from, say, here to here, and then a little line segment is created in the graph. So it makes a spirograph pattern. But in reality, of course, they are just going around. They are not, I'll show you, they're not crisscrossing. That's just a visual thing. So here's here are the ideal orbits, and you can see that they're all circular. Okay, and interior satellites are actually very close to Saturn. Okay, so thank you very much.